So we are discussing this topic, switching, today. So switching is a technique to forward a packet from node to node to reach it to the destination. Okay, so I can write the definition. It is a technique by which message switching and the packet switching. The definition of all the methods, and then we'll see how they are different, means with each other, and then we'll do some numerical on this packet switching. Okay, now to understand the circuit switching, so we'll start the circuit switch. Now to understand the circuit switching, we'll take the example of the telephone system. Now in this kind of switching, we need a dedicated channel. So in order to make the two machines possible to communicate, there must be a dedicated line or dedicated channel, then only the communication is possible. Like in the telephone system, what is happening? If the two person want to communicate, first there is a connection established between the two parties, then only they start communication. So how the things are working? If you take the scenario, let's say these are the operators sitting here. There is one line, dedicated line is there to connect the persons. Let's say there is a series of person P1, P2, P3, P4, and if any of the two party wants to communicate, if P1 wants to communicate with P4, then what is required? First it has to connect with this. This is one connection is established, line is actually available. So first it has to connect with this X1, and this has to connect with P4. Now we have a dedicated channel established, and now they can communicate. They can share the data what they want to share. So what is required here? The first thing is, in order to communicate, first they need to establish a connection. So when we find out the time requirement for this kind of circuit switching, the one task is means to set up the connection between the two parties. This is one time required. Okay, and once the connection is established, they can communicate, they can share the data, and once they have finished their job, they have to notify that okay, I have done my work, now you can disconnect, so that the line is free and other can use. So what are the advantage and disadvantage? If you look at the features of this type of communication, so what we have identified, so in this circuit switching, we have noted there is a dedicated channel. There is a dedicated interface which is only provided to the two parties, those who are involved in communication. Then second, we can comment that because this is a dedicated communication, means we have a dedicated channel is there, then because of this we can say that the communication is reliable. There is a less chance that the data will divert to other path, because we have already set up one path, so the communication is reliable. And also because we have a path established initially, so this is provide as the fast delivery of the data, so the process is fast. This is also one observation. But We also observed that once the communication is going, now if P2 wants to communicate with P3 or P4, it has to wait because the resource is already booked, it is already engaged with this communication, so they cannot use the same channel. They have to wait. So here we can say it's a costly affair because the resources are reserved. The resources which we see here, it is actually dedicated to the two parties. They are not open for the other parties when we are having the communication established. If we apply this thing in internet, if two parties are communicating, if two people are communicating, then we cannot block the entire channel, but it should be open to everyone. So this is not actually we are using in our present internet system, but it is sometimes required. Why it is required? Because of these features. Like the big companies like Google, IBM, Microsoft, what they are doing, it's not good for us to establish one line. If I want to send the data from, I am sitting here, I want to send data to some other person who is sitting in another city or other country, I cannot set my own channel. Okay, it will be very, very costly. But because these companies have dealing with the huge data, and when they want to share the data, so these companies are not using this internet. What they are doing, they are having their own personal channel. They have their own optical fiber cable. So because there's a dedicated line, so that the communication is, their data will be reached fastly. Okay, it is not shared. It is reliable, it is secure, so they can afford, but we cannot afford. And why it is required? Because if they share this internet kind of things, then it will take too much time, and that time is having a cost for them. So this is called circuit switching. If we want to find out the time, so what is the time requirement? Total time will be setup time. Setup time means the time which is required to establish a connection between the two parties, plus something called propagation time, then the next element is transmission time. Yes, propagation time, I will tell you what is this. Transmission time and the teardown time. So this is the formula we can derive: setup time, propagation time, transmission time, and teardown time. Now what is propagation time? So we can write propagation time as TP. Okay, now this is the time required to deliver data to destination. So propagation time is the time required to deliver the data from the source machine to the destination machine. This is called propagation time. Means to deliver the thing from here P1 to P4, the time required is called propagation time. And then we have something called transmission time. Time required, this is the time required to deliver all the bits onto the channel. This is called transmission time. Okay, so we'll keep these terms in mind, because we are having some numerical, and then we'll see what is the impact of these terms on the total time. Okay. Then the next is called message switching. Teardown time. Yes, teardown time is the time required to break the connection. Now why it is required? Because once they have established the connection, they have finished their work, they have to notify that okay, I have received everything, now I want to disconnect. So a kind of acknowledgement is sent to the from the receiver to sender. Okay, so it will take some time. This is called teardown time, to break the connection. It is required so that the channel can be made free and is available to the other parties. So first you have to establish the connection. Once it is established, you can share the data, and then once you have finished your work, you have to intimate that my work is finished. That is called teardown time. Means you have to intimate, you have to acknowledge the sender that I have received all the bits, and then sender said okay, I am going to break. He said okay, you can break the connection. This is called teardown time required. Okay, for this particular activity we need some time. This is called teardown time. Yes, propagation time is the time to deliver. Now let us say we have some data here. We want to send some data, right? Now this data, the time required to reach this data, that's a 200 bytes from the sender to receiver. This is called propagation time. How much time it takes to reach from here to here. Okay, this is called propagation. What is called transmission? Now when this data has to be delivered to channel, so it is actually delivered like this, means bit by bit it has to be sent to the channel. So the time required to deliver all the bits to the channel is called transmission time. Okay, let's say I want to send 1 MB of data. So how much time it will take to deliver all the 1 MB bits to this channel? This is called transmission time. Then we have something called message. Message switching. Now in the message switching, there is no need to reserve the path. We are not holding the resources. We are not holding the resources. The resources are free for everyone. Now as we have seen in this case, what is happening? Once the path is established, it is only dedicated for the two parties who are involved in communication. Other parties cannot use this. But in the message switching, what is happening? We are not going to reserve the path. It will go, means the message will go from the sender to the intermediate node, and then to intermediate node, and this path is open. And for example, let's say there are many other nodes are also possible. Okay, so it will go to here, and then from here this will decide to forward to here or here. Based on some routing table information, it has to be decided that the packet to be forwarded here or here. Okay, and from here to here or to here. Okay, so when you use this message switching, the path is independent. We have no dedicated path. The path can be of any form. It can go like this, it can go like this. It depends on the scenario of the internet. At that instant, what is the position, means how the routing table is guiding. Okay, and this is not reserved. All routers are actually open to provide service to every other packets, to every other machines. So this is called message switching. Now in message switching, if we want to find out a total time, so the time is, so we talk of setup time. Setup time is required or not in the packet switching? Sorry, in the message switching. It is not required because we are not establishing a path. The packet can take any path, right? So this time is not required here in the case of message switching. The other thing is called propagation time. Yes, this is required. Yes. Transmission time. Yes, it is required. Plus teardown time. This is not required. Means we need only two elements: propagation time and the transmission time. Now here we'll take one scenario. Let's say this is a sender and it has to go to receiver through x1 and x2. Okay. In the previous case, the path is established, but here the path is not established. Because the path is not established, so in the message switching, we need one extra information that is called header. We will take one thing that is called header, which is always required to guide the router to give the best path. Now what is happening here? Once you start the communication, because you have a defined path, you will go to here. But in this case, once your message reaches here, because there is no dedicated path, so something is needed at this point to guide where to forward. You understand? So every time when message is delivered, something is added with the message that is called header. That is the kind of information that what is the destination. And looking to this header, every router will forward this packet. So here we have extra, we have some overhead that is called header, that is to be added with the message which we are sending. So let us take some notation. Let's say message is M and bandwidth is B. Then we can say our transmission time is what? Right? Now, when I say here transmission time, I am saying the transmission from hope to hope. Actually, transmission time from here to hope. Per hope you can say. It is M by B. Or if I find the total time required for this message switching, I may write number of hopes into the propagation time. So if my number of hope is 1 hope, 2 hope, 3 hope, right? So number of hope is how much here? Let's say number of hope is L equals to 3 here. So I can write a formula here, L into propagation time plus L into transmission time. This is the formula to be used in message switching. See, this is the number of hopes. Number of hopes, right? You are doing again and again. You are doing here, you are doing again here, you are doing again here. Okay, so multiplied by number of hopes. Then we will see here that if we go with this kind of switching, message switching, there is a drawback. We are not able to efficiently utilize the bandwidth. Okay, then comes the concept of packet switching. We have some drawback with this. We will take one example. Is that what is the problem with this? This is not giving us the efficient utilization of bandwidth. Okay. So first we'll take an example. What I am doing is I am taking one numerical and I am just considering this part. I am focusing on this part. Later we'll understand why this, and I am just leaving this part because this will remain the same. Okay, this part will be getting affected in our example and you will observe this. So let's say I am using this message switching and I want to deliver some message, and message is 1000 bytes of message I want to deliver, and I am using a channel with this bandwidth. of 1 megabyte per second, or you can say 10 to the power 6 bytes per second. And the header size is given to us. This is 100 bytes is required when you send any message. That means the message which you are delivering, the packet size will become 1000 plus 100. That means you are going to deliver this much bytes. This is your size of the packet which you are going to deliver. And the hops we are considering, let's say the number of hops are, that is L is equals to 3. So if I want to find out the total time, so let us first find out the transmission time per hop, means the transmission time from the sender to the next router to the next router, and then to the receiver. So we'll find this transmission time is equals to how much? This is it okay? So this will be how much? So this will be 11 into 10 minus 4 seconds, right? Or I can say 11 into 10 minus 4 into 10 power 3 milliseconds. Is it okay? So I can say this is 1.1 millisecond. Is it okay? Okay, so now I will find the total time taken to deliver this message. So it is given by using this formula. So I will write this formula, but I will only take this component. So I am just writing this formula: L into TP plus L into TT. So just focus on this part. We'll take this as a constant, and then what we'll get? We get 3 into 1.1. This is 3.3 millisecond is required. This time is required to send this amount of message. But then it is realized, when we go with this kind of thing, we have actually achieved one thing. What we achieved? We have achieved that now the resources are not reserved. Okay, it means the path is free, anyone can use these routers. The routers are not blocked, the buffers are not blocked, the CPU is not blocked, the bandwidth is not blocked. It is available to all the elements which are a part of internet. But we will observe that by going with this, we are not going to use the concept of pipelining. Yeah, this I am just leaving it because it will be same in all the calculation. What is actually affecting to us is this part. If we want to find this propagation time, what is required? We want to find the time. Now we have a formula: distance is equals to time into speed, right? So you can find that time is equals to what? Distance upon speed, is it? So if I give you more information, what is the distance between the two hops? You can find this part also. So now we will realize that this is actually will be same for all the calculation. This part is actually going to affect us. That's why I have taken this part, and I will show you with some example that how it is affecting us. So before coming to the concept of packet switching, we need to understand why the packet switching is actually useful and why it comes into picture. There is a concept called pipelining. You know pipelining? So we'll see what is happening in the pipelining, and we'll derive one formula. In the pipelining manufacturing, what is happening? Let us consider one product is, there is one product and it is getting ready in 4 days. Means it takes 4 days to manufacture this. Okay? And further we assume that to get this product ready, it has to undergo 4 phases. Let's say phase 1, phase 2, phase 3, phase 4. So it goes 4 phases, and at the 4th day you'll get this product ready. Does you understand? So one product will take 4 days, and I am interested to get 100 products. So it will take 400 days. This is simple. This is a simple calculation. But how we can improve this? We can improve it by applying the concept of pipelining. Now what is proposed here? It is proposed that when we start this product P1, when it finishes at phase 1, it reaches to phase 2. At that time itself, you start with the second product. Okay? When it reaches to phase 3, by this time this comes at the phase 2, and you start with the third product. Okay? When it goes to phase 4, this comes to phase 2, this comes to phase 2, this comes to phase 3, and you can start with the product 4th. So what we observe that at the 4th day, you get the first product, is it?
Yes.
5th day, you get the second product. 6th day, third product. 7th day, fourth product. So what we observe? We observe that the first product will take 4 days, and then 99 product will take 99 days. Is it? That means it will take only 103 days. And if you want to find out the rate, so you can say rate will be 103 by 100. That is how much? 1.03, is it? 1.03 day per product is actually now getting ready. Earlier it was like 4 days per product. Now it is approximate 1 day per product. So we have seen that the things are improving. Now the same concept is applied here. Now in what context it is applied here? Now if you observe, if you send, let's say here I want to send 1000 bytes of data. So 1000 bytes of data will be transmitted from here to this channel. It will take some time. And then it has to deliver from here. Again it will take some time. Now when you are transmitting this data from here to the channel, actually all the routers are doing nothing. But if you divide your data into parts, and if one router is having data here, other router is having data here, when it is going to transmit, this is also transmitting the data. So we can improve in the time. We can, improve the value of this transmission. Thoroughly, we are transmitting the data. Is that okay? Now, by using this concept, we can deduce one formula. What is the formula? Formula says now the total time now we'll look to the packet switching concept. So in packet switching, what is happening? We are not sending the entire message as a one go, but we are dividing it into many small packets and then delivering it. What does that mean? It means if I want to send 1000 bytes of data, I may be sending 500 MB, okay? Sorry, 500 bytes, something like this. Or I may make 10 packets or 20 packets, this will depend. But I am sending in some small chunks. So let's say number of packets I have, that is n. I have decided to send my message using n number of packets. So I can come up with new formula. What is the formula? Formula says total time will be L into propagation time plus L into transmission time plus n minus 1 into propagation transmission time. Now again, so here we have observed that when we have used this message switching, then the transmission time component is this much, 3.3 milliseconds. This is the component of transmission time. So again we'll focus on this transmission time and see what is the impact and how it is affecting the entire performance. Okay, so take us first example. We'll take first example. We have decided to make the entire message divided into 5 packets. Okay, so number of packets is now this. We have decided to send the message in the form of 5 packets. Then what is the size of the packet? Size of packet will be what? It will be 1000, and also we are assuming that header will be of 100 bytes, so this will be 1000 by 100 plus 100. Is it okay? Yes. So this will be how much? 300 bytes is actually there. Now keeping in mind this is the size of the packet, then what is the transmission time? This will be what? 300 by 10 power 6. How much? So you can write 3 into 10 power minus 4, is it? Or you can write this is 0.3 milliseconds. Now, keeping this value, we will find the total time. We will find the transmission time, actually, total transmission time you can say. Total transmission time will be how much? It will be, how many hops we are having? Here the value of L is 3. We are having 3 hops. So 3 into 0.3 plus 4 into 0.3 will be how much? 0.9 plus 1.2 will be 2.1 millisecond, and we have seen that we have observed a better value for transmission time. It was like 3.3 for the same amount of data, but now when we have divided into 5 packets, it is coming to 2.1 milliseconds. Okay, but again there is one question: how to determine what must be the size of, how many packets we need to make. This we have understood, that packet must be divided, but how many packets? 5 packets, 20 packets, 30 packets. Is it always better when we make more packets? No, there is a threshold. Up to some limit it will give you a better performance, but when you cross the limit, when you go beyond that value, it will degrade the performance. So we'll see with some example, and then we will make a comment. So the same thing we are doing with the 10 size. Now my 10 packets, yes. So the same thing I am doing with the 10 packets. So my number of packets will be 10 now. So again, if we go with this, what we will observe, the size of packet is how much? Is equals to 110, 200 bytes. And then what is the transmission? 0.2 milliseconds will be the transmission time per hop, and if we want to find out the total transmission time, total transmission time, we will use the formula that is 3 into 0.2 plus 9 into 0.2, and this is 0.6 plus 1.8, this is 2.4. So what we have observed? We have observed that still it is better than this, but now the performance is not improved. It is a 2.1, but it is 2.4. So we need to find out what is the, how many packets we need to find out. Up to how much time we need to keep on dividing into packets. Will it always be improved? Now see, we have seen, though it is not improving the performance, but it is still better than the previous one. Still we can comment that this 2.4 is far better than 3.3. Okay, will it be always better? We'll check. Now the number to determine the size of the packet. How to find out? But we have some defined procedures. We have some defined packet sizes also given in the theory. So this is a packet size which is said to be a best size for sending over the internet, but again this is not always best and it is not always working. We have many other criteria, conditions that guide us that why this is not best, but it is suggested. So the packet size, this is the suggested value. This is the packet size suggested. Okay. 65535 bytes is actually said to be a good size for a packet, but this is not always working. Again, why it is not working? Because the packet size determined by the two main factors, that is by the MTU and MSS. We will discuss this also, MTU and MSS, but I'll give you some introduction. MTU is said to be maximum transmission unit, and MSS is said to be maximum segment size. Okay, now these two things guide the actual size of the packet to be delivered over the internet. Now what are these? One more thing, MTU is actually governed at the data link layer and MSS is governed at the transport layer. Okay, so we have two concepts of defining the size of the packet before it leaves to the machine. So when actual data comes to the channel, before that we did so much work based on this information, MTU and MSS, at this layer, data link layer and the transport layer. Okay, now what is happening actually here? We have the concept called segmentation and fragmentation. Okay, segmentation and fragmentation is both are actually dealing with dividing your data unit which is actually we want to deliver, the actual message which you want to deliver, the application layer that sends the data which is to be delivered. But when it goes to transport layer will did some segmentation. Segmentation means it will divide the entire data unit into some parts, small parts. And later when it goes to data link layer will always look to this segment, mean the size of this, and then it, while consulting with the data link layer, the network layer may also guide to do the fragmentation. Fragmentation is also one activity of dividing into smaller part. Segmentation is also an activity of dividing into a smaller part, and both are acting at the different layers. Segmentation is acting at the transport layer with the concept of MSS, and the fragmentation is happening at the network layer with the consultation of MTU. Now why it is required? We'll take an example. I'd like to share one example. There are two persons there. Let's say this is one shop is there, okay, and this is one customer of this. This is one company, you can say, one shop or company which provides some items, right? This is a customer. Now customer ordered some product. He says, I want to purchase one product from you. Let's say the P1 is the product that the customer is interested. So customer says, okay, I want to purchase this. Please deliver this product to me. But at the same time, customer says, when you send this product, means you are sending in one wrapper, right? Kind of packet. So it will say that please send me in a envelope or in a carton. The carton size should not be more than 4x7 because my gate is actually not more than this. So you please, when you make a packet, when you keep my product in the packet, your packet size should be this much. You understand this? Yes. So this information is given by customer to this person, and he will take care of this. He will keep this in mind that the product should not be more than 3x4, something like this, okay? Because it is not allowed to enter through the gate. But then it has made a packet of this much dimension, and then he asks to one taxi person that please deliver this to this customer. So this taxi person says, okay, I can take your item, your data, but my taxi is having the small boxes. Please don't give me big boxes. I can only carry the item of this much size, only 2x7. You understand this? Actually, the item has to carry it to this place, but through this taxi. But taxi person is saying, I am having a carrier, I am having some boxes that can take your item, but my box size is very small. So please make sure your item must be this much size. This is okay. I will do this 2x7. This is a kind of segmentation which is consulted from the customer, and this is this is called fragmentation, which is consulted with the help of the network capacity. Actually, each network is having a different kind of capacity that can allow the packet to be traveled. So this is how the things will work. Also, this is actually happening now. Why it is required? All the machines always try to make this packet of the smallest size, because fragmentation is something which is not required. With the fragmentation, many things are happening. Let's say the machine delivered any packet, and when it goes to network, let's say somewhere in the mid, the network says, I will not take your packet of this 500 bytes because I will allow only 400 bytes. Then what it will do? Now it has to decide. Now either the router will actually divide this packet into a small size, or it will say go back. So how it is decided? It is decided based on some information which is there in the header. We call it do not fragment. So when we study about the packet format, there is one bit that is set for fragment or not fragment. So if any packet is coming to the router which is of larger size, then router will look to this bit. If it is set 1, that means do not fragment, then router say, okay, discard, I will not allow you to go back. But if it is not set, then router will fragment into smaller size and then forward. But again, at the receiving end, it has to do a lot of exercise to assemble all these fragments. So this is how the things works.